The advantage of CAD modeling is that you can pre-fit very complex assemblies in virtual space, and you can catch interferences and find problems and make sure that things are going to go together in the real world without actually having to make a prototype. So we 3D model our components. We use that to generate machine code to then computer cut, whether it's a plug to make a mold to make a composite part, or a metal fitting, or a plastic accessory or fitting. So that's all created in virtual space first. Now the next level beyond that is to analyze the structural properties of the part, which is called finite element analysis. Basically an off-the-shelf product that you can get, but you can then add to it and customize it and use that to predict how stress is going to be distributed in a part, and that can then help you to make sure you have the correct amount of material where the stress is, and you can take away material where the stress is lower. Now, because we're also doing an analog of finite element analysis is computational fluid dynamics, where you take an object in a virtual fluid that's broken up into little discrete chunks, and the program resolves how the pressure fields are going to behave as all these little chunks of fluid interact with each other. Now, putting those two together, you can create an iterative loop where you take a part, you run it through CFD, it figures out the forces that are going to be imparted by the fluid. Those forces are then run through finite element analysis, and the finite element analysis tells you how that part is going to deflect. Now, the deflected shape is going to be different to the original shape, so it's going to behave differently in the fluid. So there's a loop that you can go through until you find an equilibrium where the deformed shape is actually looking the way it will when it's actually in the fluid, and you know the stresses associated with that. The deflection that's going to occur in the part is taken into account when you're designing the aerodynamic shape. So that's sort of the holy grail in the sense of being able to predict how the deformed shape of an object and the stresses in it when it's actually in use. Now, the next level above that is to be able to iterate shapes and to take away material and keep going back and forth until you have an optimized shape. You can either do it manually, where you'll try one, you'll say, okay, it looks like if I change this, then it's going to do something differently, and you'll go through. And that's obviously a very time-consuming process. So the next step beyond that is basically something called genetic algorithms, where you're effectively randomly letting a program make adjustments to certain parameters. It'll analyze the adjusted shapes, and it'll pick the ones that have the properties that you want, and it'll change those again, and it'll go through and basically gradually or cumulatively make those changes until it comes to a part that's optimized, and that tends to produce very organic looking structures, and that's all done before you actually make a prototype. Autodesk suits that cover all of these different requirements, and there's a team there that's constantly developing the software that's looking after our requirements. Part of the R&D and the advancement of the state of the art is being able to use this software and at the same time have a dialogue with Autodesk for how it can be improved, how it can be developed, and how it can meet any requirement.